In this video, we're going to derive the fundamental theorem of calculus, part 1. And so the first thing I'm going to do is I'm just going to make a sketch of some function. All right, and so our function is going to just look something like this. Right? So this right here is just going to be our function, and we're going to say that this function is y equals f of t. And you're going to see why we're using the variable t instead of x in a moment. But pretty much, we're just going to say that this is the t-axis and this is the y-axis. Now, we already understand the idea of an integral. It's pretty much just the area underneath the curve. And so we're going to say we're finding the area underneath the curve of this function from a, right, from this value a to some value x. Okay, so the area underneath the curve would pretty much be this area right here. So this would be the area underneath the curve. And so the way that we could represent the area underneath this curve right here as an integral is, well, we would say that this is just the integral from a to x of f of t dt. And we're going to say that the area underneath the curve right here, we're going to say that this is actually a function, g of x. And so what we're actually going to do is we're going to let x vary. Okay, so x is actually a variable here. And so if we vary x, we're going to keep a constant. So a is a constant, and we're going to vary x. And so the whole idea of that is that if we vary x, then we're varying the area underneath the curve. And so the whole idea of the fundamental theorem of calculus part 1 is, what is the rate at which area is accumulated underneath a curve? And we're finding the rate at which area is accumulated under the curve, then all that really is it's the derivative of an integral. So that's the whole idea of what we're doing. Okay, so we're letting x change. So really what we're going to be finding is g prime of x. And so when we're finding g prime of x, pretty much it's just the derivative of this integral. So the derivative with respect to x of this integral right here, from a to x, f of t dt. So then how do we find the derivative of something like this? Well, to find the derivative of anything, we know that we could just express it as a limit, right? We could just write the derivative as a limit. So we could say this is the limit as h approaches 0, right? And we remember that we would go from a to, it would be x plus h f of t dt minus the integral from a to x of f of t dt. So this right here, pretty much x plus h and x, as like we remember from derivative as a limit, all divided by h. So this right here is how we could write the derivative as a limit. So then how do we actually evaluate this limit? Well, notice that on the top, pretty much notice in the numerator right here, all we're really doing is we're subtracting two integrals. So really, that's the same thing as subtracting two areas. And we're going to say that x plus h, right? So this is x. Then we're going to say that x plus h is pretty much like right here. We're going to say that x plus h is right here. So we're going to call this x plus h, right? And we're going to say that this area right here, pretty much the area from a to x plus h, the area from a to x plus h is this area, right? This area, right, all the way through here, right? And so this right here would be the area from a to x plus h. Now, if we were to subtract the area from a to x plus h minus the area from a to x, that means we're subtracting the area from a to x plus h minus the area of x, then we're going to get the area from x to x plus h. And so that's really what we're going to get. We're going to get, we can just rewrite this as g prime of x, right? It's the limit as h approaches 0. And so what we get is the integral from x to x plus h of f of t dt. Right, so that's what we would get. Right, and this is, of course, still all divided by h. So then what do we do from here? Well, check this out. It turns out what we've actually got here is actually really interesting. We know that all the denominator is, right, the denominator right here, h, we know that this really is x plus h minus x, right? It would be that. And so notice what? This is actually the average value of our function from x to x plus h. So it's really the average value of the function from x to x plus h. And so we're just going to say that the average value of our function from x to x plus h, we're just going to say it occurs right there. This is where the average value of our function is, right? It's right here. So this line right here, that represents the average value of our function. Now, that means the average value of this function, it occurs at this x value right here. And we like to say that the average value of our function occurs at this x value c. So this is where the average value of the function occurs. And so if this is where the average value of a function occurs at x equals c, then our average value would be f of c, right? Because just the actual function value of that. Okay, so now that we know that, pretty much what this really is here, the average value of our function is just f of c. So that's really what we get. So we can now rewrite this as g prime of x equals the limit as h approaches 0 of f of c, because that is really what that is, average value of our function. So now the whole question that we have to answer is, as h approaches 0, what does f of c approach? Well, in order to figure that out, pretty much the idea that we have to know is that c is always in between x and x plus h. So really, c is always between x and x plus h. And so this idea right here is really important in understanding how we figured this limit out. And so since this is always true, we know that as h approaches 0, then x plus h is going to approach x. So x plus h is going to approach x. And since c is always between x and x plus h, c must approach x with it, right? C must approach x as well as x plus h approaches x. And so c is really just going to approach x. And so as a result, if c approaches x, then f of c must approach f of x. And so as a result, that would be the answer to our limit. And so what this really is g prime of x equals f of x. This is the answer. How cool is this? So really, g prime of x is the derivative of our integral, and the derivative of the integral of our function is equal to the function itself. And so what this really means is that the rate at which area is accumulated by our function, so the rate at which area is accumulated is equal to the actual value of the function itself. So for example, if we were to just choose this point right here, the rate at which our function is accumulating area at this point is equal to the actual value of the function at this point. And so that's the whole idea of the fundamental theorem of calculus part 1. Pretty much the idea, we're taking the derivative of an integral of our function and we get back our original function. And so this kind of gives us the relationship between derivatives and integrals. And so yeah, this is the whole idea of it all. So this right here is the fundamental theorem of calculus part 1. That's it.